Welcome back to Discovering Geometry with Mrs. Berry. This is lesson 28. Today we'll be looking at isosceles triangles. Specifically looking at, are there any special lines of symmetry in isosceles triangles? First, I want to consider a scalene triangle. We're going to maybe use the triangle ARC. In this triangle, where is the altitude? So the altitude is from C down to D, because that's at a right angle from the base up to the opposite angle. And then where's the median? CF is the median. It bisects AR. So the AF is congruent to FR. And then the angle bisector is CE. Could any of these segments ever be the same in a triangle? What if we draw ARC with a shorter base, a shorter AR? Then where are the altitude, median, and angle bisector? Well, we can see that FC and EC and DC get closer together. Here's our original one. See how there's some space? We get them closer together when we shorten AR. So could they ever be the same line? What would our triangle look like then? Let's look at our investigation and see if we can't figure this out. We're going to construct two different size isosceles triangles. Label them ARK, with K the top at the vertex angle. Then you're going to construct the angle bisector, drawing a new point D that's on AR. Then we're going to compare AD and RD and see, is D the midpoint of AR? If it was the midpoint, what would that make the line KD? Would that make it the median? Compare the measures of angle ARK to RDK. What conclusions can we draw about that? So here is the video. I have point K and I'm going to make an isosceles triangle. And to do that, I can just draw an arc because my arc is going to be equal distance. And then I can draw my lines anywhere as long as they touch the arc. They're going to be the same measure. Then I'm going to draw my base and label it AR. Now my angle bisector is what I'm going to draw first. And once I get my angle bisector, I'm going to label the point that it touches at D. Now I'm going to compare AD and DR, and they're equal, so that makes it also the median. When I look at the angle ADK and KDR, I get right angles, so they're the same. And if they're right angles, then that also makes it the altitude. So you can see we have the angle bisector and the altitude and the median all in this line KD. So what does that mean? Our vertex angle bisector conjecture. In an isosceles triangle, the bisector of the vertex angle is also the what? It's also the altitude. And what else was it? It was the median for the base of the triangle. So all three of those lines were the same line in an isosceles triangle. Back from our first picture, we were trying to get all those lines the same. If we had shrunk that base so that the other two sides were equal length, it would have been an isosceles triangle, and all three of those lines would have been the same one. What about equilateral triangles? Have we noticed that an equilateral triangle also has equal angles? A triangle with three congruent angles is called equiangular. Could we prove that an equilateral triangle is also equiangular? How can we prove that? Well, what did the isosceles triangle conjecture tell us? Back from lesson 23. It told us that when we had an isosceles triangle, that the base angles were congruent. So are all equilateral triangles isosceles triangles? Yes, our definition of an isosceles triangle is at least two sides the same length. So an equilateral triangle has three sides the same length. All equilateral triangles will be isosceles. Are all isosceles triangles equilateral? No, isosceles triangles only have to have two. Equilateral triangles have to have three of the same length sides. So not all isosceles triangles are equilateral. But when we have an equilateral triangle, then we know that all of the sides are the same length. So A, B, C. AB is congruent to BC is congruent to CA. So if AB is equal to AC, AB is equal to AC, what does that tell us about angle C and angle B? Well, the isosceles triangle conjecture would tell us that these base angles would be the same. So could we keep going around this and make some more proofs out of this? So if AB and BC are equal right here, then that means that angle C would be congruent to angle A. And if we keep going, if CA is congruent to CB, then angle B is congruent to angle A. And we could go round and round because all three sides are congruent, then all three angles would be congruent because we could keep turning it and using a different base. So then the base angles would all be congruent. So we do have a conjecture for that. Every equilateral triangle is equiangular, and every equiangular triangle is equilateral. So they go back and forth. For this conjecture, the converse is also true. That makes it a biconditional conjecture. That means that a triangle is equilateral if and only if it's also equiangular. And it's equiangular if and only if it's equilateral. Either both conditions are true or neither is true. So because it's biconditional, you can go back and forth. The converse and the conjecture are both true.